Okay, so now that you know how to write SPDF notation, right, which is basically a cataloging of all the electrons in an atom, we're going to do that again, but we're going to do it visually. These are called orbital diagrams. And there's actually a benefit to doing it this way, and you'll see that by the end here. Okay, so first off, these are just pictures, right? So they're going to follow the same rules, right? The manner of fill is the same. Okay, that means the same fill order. Right, with the arrow diagram, 1s, 2s, 2p. Okay, you're still going to follow that. You're still going to follow the rules about how many electrons can be held in s, p, d's, and f. Right, so s is 2, p's is 6, d's is 10, and so on. Now, the additional requirement has to do with creating a stable arrangement, and I'm going to explain what that means. So let's just jump right into an example of nitrogen. So this is nitrogen's SPDF notation, right? That should look familiar to you. There's 7 total electrons. Now, the orbital diagram is the exact same thing, except if you recall that in an s orbital, there's only, in an s sublevel, there is only one orbital. So I'll put one circle there. Now there's 2 electrons here. Now the electrons that are placed in the orbitals are going to be represented with little arrows. Right? So that's the first arrow. That represents the first electron in that sublevel. And then I draw a second arrow, but I draw it facing downward. Okay, and this is for balance. The electrons that are both present in the same orbital, they must be spinning, so to speak, in opposite directions for balance. Okay, so let's just add a little rule here. It's called the Pauli exclusion principle. All right, and it states that the electrons in the same orbital cannot spin in the same direction. That's why one of them, the first one, is always going to be pointing up, and the second electron in the orbital will be facing down. Okay? All right, so that was 1s. 2s, being that it is an s, is also going to have just one orbital, and the 2 tells us there's 2 electrons in it. So the first arrow goes up, and the second arrow goes down. 2p has 3 orbitals, because remember, p, 3 orbitals, 6 electrons. Now, the number of electrons in this sublevel is 3. Okay, but I'm going to jot something down here. I don't want you to copy what I'm doing because I'm going to erase it in just a second. Okay, but watch. Let's say that I put 3 electrons in this sublevel here in green, like that. So, here's the problem. In this situation, you have 2 electrons that are both in the same orbital, but there's this empty orbital over here. Electrons all have what kind of charge? Negative charge. And whenever you put 2 things with the same charge near each other, they're going to repel. They're going to push away. So the fact that 2 negative electrons in the same place, right, they're going to be bumping into each other, they're going to be pushing each other, and what's going to eventually happen is one of these electrons is going to get pushed over here. And once it goes there, it's actually going to stay there. So what we learned from this then is the electrons will not share an orbital unless they have to. If there is an open space for them to go, then they will go there. And this is what we call Hund's rule. Hund's rule has kind of a technical definition. It says the lowest energy configuration is one having the maximum number of unpaired electrons. Well, if you look at this sublevel right now, how many unpaired electrons do you see? 3. All 3 electrons are unpaired, right? 3 unpaired electrons is lower energy, and when we say lower energy, we mean stable, more stable. Less clashing. So Hund's rule says electrons will spread out and they will not pair up unless there's no other option. Kind of like when your family moves into a new house, right? And let's say that there's 3 children and there's 3 bedrooms. You are all going to choose to have your own bedroom, right? You're not going to pair up just for the fun of it, right? You're going to want your own space. And electrons are the same way, right? But maybe they're not as messy as you. Okay. So let's look at another element. This is oxygen. 1s2, 2s2, 2p4. Okay, so as you can see here, here's the 1s2, there's 2 electrons there. Here's the 2s2, there's 2 electrons there. In 2p, we have 4 electrons. So because there's only 3 orbitals, the first one, the second one, the third one, and this guy here facing downward, he's the 4th one. Now he has to go into the first orbital and he must be facing down because there's no other place for him to go, and the spin must be opposite. Okay, so when we place electrons, we put them in one at a time, and if there's multiple orbitals, we go from left to right, and then if we need to, we come back and we do it again. But the second time round, the second electrons placed in these orbitals will be facing down. So, let's try some more examples. All the orbitals, let's get through this here first. All other orbitals in a given subshell are considered equal in energy. What that means is that these 3 orbitals here, they're all equivalent as far as energy, as far as distance from the nucleus. But these guys and this guy are not totally equal. I know they're both in energy level 2, but do you remember that chart which showed which one was closest to the nucleus? How this was slightly closer than this was? Okay, so there's a difference, right? If they're in the same energy level, they're close, but there's still a slight difference. Okay, so let's do a couple of these just to kind of reinforce this. Sodium. Sodium has 11 electrons. All right, so 1s2, and as I do this, I'm going to draw circles above. 1s2. 2s2. 2p6. 3s1. Okay, so let's go ahead and fill them in. Starting from left, this first electron is the 1s1 electron. This second guy here is the 1s2 electron. Then we have 2s1 and then 2s2. Okay, so now watch. As we fill in the 2p6, left to right, one at a time. 1, 2, 3, 4, 5, 6. And that's a total of 10 so far. I have 11 electrons. That last electron goes in 3s. And that is our orbital diagram. Now, any rules that we've used for SPA differentiation also apply, which means we can also do shorthand. Shorthand is a great way to save yourself from drawing lots of circles. So, chlorine, for example. Let's do the shorthand for chlorine. You remember how to do that? So find chlorine on the periodic table. Find the bookmark which comes before it. What element would that be? Neon. That is neon, right? So let's go ahead and write neon in brackets. Okay, neon is what? Is it what p block is it? P row is it? Is it 2p, 3p, 4p? What is it? Okay, it is 2p. So if neon is 2p, then according to your arrow diagram, the thing that follows 2p is S, 3s. Okay, so neon had 10 electrons. Chlorine has 17 in total, so we got to work our way up to 17. So 3s2 brings us to 12. And then after 3s comes 3p. A p suborbital has 3 orbitals, and there's going to be 5 in there. So 1, 2, 3, 4, 5. And we are done. Vanadium. Vanadium is 23. 1 second. Okay. So let's do shorthand for vanadium as well. So vanadium is 23. The bookmark which comes before it is what? AR. Okay, so argon is 18 electrons, and argon is 3p. So after 3p comes what? 4s. So if we do 4s2, that brings our total to 20. We have 3 more to go. And after 4s comes what sublevel? 3d. Now d's have 5 orbitals. So you got to write them all. I'll draw all 5 circles. This is 3d, and the number of electrons that we'll be putting in there is 3. So since there's only 3 electrons to put in there, well, actually, let's fill up the 4s first. So here, let's fill up the 4s. That's 20. And then here's our d's. 1, 2, 3. And we're done. We don't have enough electrons to fill up that sublevel, but that's okay. Right? Most elements do not have enough electrons to fill up their sublevels. At least not the last sublevel. Okay, take a couple minutes and do the last 2. You probably don't need shorthand for these. You could if you want, but... Okay, so let's try the first one. So carbon's got 6 electrons. 1s2, 2s2, 2p2. First orbital, second orbital, and then 1, 2. You guys get that? All right. And for neon, 10 electrons. 1s2, 2s2, 2p6. 1, 2, 3, 4, 5, 6. How we doing? Okay, so orbital diagrams are just pictures of what you've done. The only difference is when you draw your circles, you just got to go from left to right when you fill in the sublevels. All right, so you got to make sure that you have the most unpaired electrons as possible. Okay, we have already talked about shorthand diagrams, but let's talk about a new term, paramagnetic. Paramagnetic is an element that is affected by a magnet, meaning you can hold a magnet to it and it will respond. So elements that have unpaired electrons, unpaired, they're going to be paramagnetic. But if they have only paired electrons, that's diamagnetic, unaffected. So, if we look at the examples we just did, you're looking for the elements with unpaired electrons. Those are the ones that can be affected by a magnet. So which elements would, well, let's turn this around. Is there any element here that will not be affected by a magnet? Neon, because all of neon's electrons are paired. So this is what we call diamagnetic. Whereas all of the others have unpaired electrons, they will be affected by a magnet. Now, some more than others, right? You can't, a magnet's not going to like really pull all these towards it very strongly, and we'll demonstrate that a little bit later. But basically just look at the orbital diagram and you should be able to tell whether something is or is not. Is it diamagnetic or is it paramagnetic? Okay. Okay. So we're going to talk a little bit about the periodic table. This was the original periodic table that you're looking at here. This was first conceived by Dmitry Mendeleev, a Russian chemist, and he was studying the elements, and they knew the atomic masses for the elements at the time. They knew what the masses were. And so he organized them based on his experiments. Essentially, he observed reactions. And in the first elements here, the first column here, lithium, potassium, rubidium, cesium, he noticed that they react very eagerly with water. And he put them in the first column. And then he noticed that some other elements sort of reacted, beryllium, magnesium, calcium, they sort of reacted with water. And then not so much in the middle, but then he noticed that elements started reacting, becoming reactive again, like oxygen, like fluorine. And then there was a drop off, and then at the end of the row, it started over again. So the reactivity followed a predictable pattern where it was started off being really reactive, non-reactive, reactive, and then started over again. Really reactive, non-reactive, really reactive. So this pattern allowed him to organize these in a grid, but not all of the elements were discovered yet. So anytime you see a dash, that is where an unknown, an undiscovered element might be. But because he arranged the elements this way, because he saw that, well, these guys in the same column all react the same way, then I predict that whatever element is found here is going to react just like these guys, and maybe a little bit like these guys. And it turns out that he was right. He used repeating patterns to predict the properties of unknown elements. Okay, so this is what we call periodic law. Chemical and physical properties vary in a periodic way. Repeating. Periodic is another way of saying repeating. Now, the periodic table was arranged originally by mass. So Mendeleev's was by mass. Later on, they revised it and changed it to atomic number instead. So the periodic table you see on the wall, it goes in atomic number order, right? But they didn't. They just used mass initially. So terms. Periods are the horizontal rows. Horizontally, any one of these from left to right is a period. All right. So far on the periodic table, I've called them energy levels. So the periods mean energy levels. Families or groups are vertical columns, up and down. So if you look at the periodic table and if you see the elements, well, here, let's use the last column that we've been using for bookmarks. What are the elements in the last column? They have a name. Yeah, they're called the noble gases: helium, neon, argon, krypton, xenon, radon. If they're in the same vertical columns, they're going to have the same. I shouldn't say same. I should say similar. Yeah. Similar reactivities, similar properties. Now, the families are numbered, and depending on which periodic table you look at, you might see that they have numbers like 1, 2, 3, 4, all the way through 18. Or you might see Roman numerals with a combination of Roman numerals and letters. Or you just might see, numbers with letters. The numbering is not entirely agreed upon. They have different systems depending on essentially which country you live in. I'm not so concerned with the numbers. Okay, and the reason why we don't really care about the numbers, as long as you understand if they're in the same family, they will have similar properties, then I will call anything underneath nitrogen the nitrogen family. I will call anything underneath carbon the carbon family. Can you look up and tell me what elements are in the carbon family? Silicon, germanium, tin, lead. Okay, so we're going to worry so much about the numbers. Okay, so there are 4 main families that you need to know for sure. We will be referencing them a lot. The first are the alkali metals, which is the very, very first column. If you look at that first column, the alkali metals, by the way, do not include hydrogen. So besides hydrogen, we are talking about lithium, sodium, potassium, rubidium, cesium, francium. Those are called the alkali metals. So you need to know that's their name. The second column you need to know, they're called the alkaline earth metals. Notice the name is similar but not exactly. All right, alkaline earth metals. This is the second column. So here we're talking about beryllium, magnesium, calcium, strontium, barium, radium. Okay. Then we're going to jump over to the far right side of the periodic table. We're going to go to we'll do the last column here first. We already mentioned these guys. The last column, noble gases. So helium, neon, argon, krypton, xenon, radon. And then the second to last column are called the halogens. The halogens would be the fluorine, chlorine, bromine, iodine, acetine. Now, I know I'm writing these out, you don't have to memorize which elements are in these families. You just need to know which column, what they're called. You'll always have a periodic table to use, right? But the periodic table does not tell you these are called the alkali metals, these are called the halogens, right? So you have to know the first two columns, last two columns, okay? All right, and then there's the middle section. That whole middle section, columns 3 through 12, these are called the transition metals. And so here we go. This section right here, the transition metals are this middle sunken 10 column area. This area has another name. Anybody remember what it's called? This is the D block, right? If I combine the alkali metals and the alkaline earth metals, what are those called together? Over here. That's the S block, right? And then our noble gases. And our second to last, which were the halogens. Okay, so these guys down here at the very bottom, remember how I said that these guys were supposed to fit in right here? How they were pulled out just to make the periodic table a little bit more aesthetically pleasing, a little easier to read. These guys are called the inner transition metals because they have to be placed back in. Now the two of them collectively are known as the F block. There's two rows in the F block. They have another name. The 4F, the first F here, the 4F is known as the lanthanides. The second F is known as the actinides. And the reason why they have those names is because it's named after the element that starts that row. Lanthanum, actinium. Those names are not really important. I'm not really going to hold you to those. Okay, just know that that whole thing is called the inner transition metals. All right. So then, probably the most important line on here is this red line, which does not, I don't think it's written on your periodic table, or if it is, it might just be black and white, it might be kind of hard to see. This red line is our staircase. And the significance of the staircase is that it separates all of our metals from our non-metals. Okay, so anything to the left of the stairs is considered a metal. Anything to the right of the stairs, oh, let's change the color. Anything to the right is considered a non-metal. So if everything to the left of the stairs is a metal, what does that mean the inner transition metals are? They're still metals because they're called inner transition metals. Plus, look at where they're placed. Aren't they? They're placed here, right? Which is still to the left of this stair. So this whole bit, okay? Now, I'm going to say there's an exception here. Hydrogen is not a metal. Hydrogen is placed there because it has the same number of electrons in its configuration as lithium, sodium, but it's not really a metal. Okay. Then, if you're okay with that, now we need to talk about elements that are touching the line. These guys here, they're essentially the cutoffs, right? They're between the metals and the nonmetals, which means they are not metals or nonmetals. These guys are what we call semi-metals. Sometimes they're called metalloids, if you're British. So the semi-metals have some properties of both metals and nonmetals, so they're in between. Now notice there's one element I didn't really highlight there. Aluminum. I didn't highlight aluminum because aluminum does not really have non-metallic properties. It's mainly metal, so it's not really considered a metalloid. It's just considered a through and through metal. But pretty much everything else there that's touching that staircase line is in between. Okay, so at this point, if I gave you a periodic table, could you label the alkali metals, the earth metals, the halogens, the noble gases, the transition metals and intertransition metals? Okay, all right. Here's another colorful picture. Okay, we're gonna pause here because we need to get into the lab.